Okay, I guess we're ready to go, and it's a great pleasure to welcome Yayu Wang from Tsinghua University, who's going to be telling us about some of his recent work on two-dimensional physics in collaboration with Qikun Zhu of Tsinghua. He'll be telling us about quantum anomalous Hall effect and interface superconductivity in two-dimensional systems.
Okay, thank you. It's a great pleasure to attend this nice symposium. Qikun is supposed to be here, but he has an urgent task, so he had to cancel his trip to the US. So he asked me to convey his apology to the organizers and also the audience. So in this talk, I'm going to talk about two different phenomena in two different 2D systems. The first one is quantum anomalous Hall effect in a magnetic topological insulator, and the second one is interface superconductivity in ion selenide grown on SrTiO substrate. Both of these projects are the result of very large collaborations. For the quantum anomalous Hall effect, it's mainly the collaboration between Qikun's group and Professor He Ke, a member of his group, who really grew the materials using MBE, and my group who did the transport on these samples. And the interface superconductivity was led by Qikun also, and the two junior faculties, Yayu Wang and Xu Ma in his group, were in charge of many of these measurements. We all, of course, the people who did the hard work are the excellent students in Tsinghua, and we have many of them. And we also benefit a lot from collaborations with many people around the world, especially for the first project, Shosheng Zhang and Jing Wang from Stanford, Chaoxin Liu from Penn State, and Pei Tang and Wenhui Duan from our department. For the second project, mainly Ziak Shen from Stanford, Donghai Li, Jian Wang from PKU, Xinjiang Zhou, and Donglai Feng, two ARPES experts. So here's the outline. In the first part, I'm going to first show you the experimental observation of the quantum anomalous Hall effect. Basically, it's a prelude for somehow to Professor Kan Wang's talk. Then I'll show you some very recent progress on quantum anomalous Hall-based phenomena. Then in the second part, I'll show you the interface high-temperature superconductivity of a monolayer of ion selenide on SrTiO substrate. So here's the original motivation. It's an old question, as Duncan mentioned. The question is, can we have quantum Hall effect in zero magnetic field? This is the picture for the quantum Hall effect in high magnetic field, where the magnetic field creates discrete lambda level, localized bulk state, and have this dissipationless chiral edge state, which give you the quantum Hall conductance. Then in zero magnetic field, it seems too good to be true. Even without magnetic field, somehow the bulk is still insulating, and there's still chiral edge state propagating along the sample edge. And from the experimental point of view, it means even in zero magnetic field, there's a finite Hall resistance, and it's quantized. It's around 21.8 kilo ohm. So you know this loop is called the anomalous Hall effect. So this quantized version is called a quantum anomalous Hall effect. This is a further theory about that by Duncan in 1988. But as he said, it's a toy model. He never imagined it could be realized experimentally. 20 years later, Chaoxin Liu and Shosheng Zhang proposed that in mercury telluride, this was at that time was recently discovered by Professor Mollenkamp's group to be a 2D topological insulator or quantum spin Hall insulator. Chaoxin proposed that if you can make this material ferromagnetic, it could be a good material system for realizing quantum anomalous Hall effect. At that time, Chaoxin was still a student in our department. And 2 years later, Zhong Fang and the Xide's group from IOP in Beijing proposed that the 3D topological insulator, bismuth selenide, bismuth telluride, and antimatter telluride, could be even better system for quantum anomalous Hall effect, because this material can become ferromagnetic even when it is insulating. I think that's a problem for this system. Somehow, it still cannot be spontaneously ferromagnetic yet. This material they propose are topological insulators. So there's a very simple diagram showing what is a topological insulator and its consequence in quantum anomalous Hall effect. So this is the band structure of a normal insulator, and this is a topological insulator with inverted band structure. Because they belong to different topological classes, at the boundary between them, the gap must close. So there's a topologically protected metallic boundary state. For 2D topological insulator, it means there will be helical edge state around the sample edge where you can see the quantum spin Hall effect. And for 3D topological insulators, there will be this Dirac-like surface state surrounding the whole sample. In order to realize the quantum anomalous Hall effect in a topological insulator, there are 3 requirements that has to be met simultaneously. First, the sample has to be topological, so there will be surface state or edge state without strong magnetic field. Secondly, the sample has to be ferromagnetic, so that you will have an anomalous Hall effect, even in zero magnetic field. And also, the ferromagnetic order will open a gap at the direct point of the surface state, so only the edge state will be left. Thirdly, the material has to be truly insulating. That means you have to tune the Fermi level very accurately into the energy gap on all the other states, and in the end, only chiral edge state will contribute to transport. So what we are looking for is a ferromagnetic topological insulator, and it's not easy to get that because we know that most insulating materials are not ferromagnetic. Very few of them are. Secondly, if the ferromagnetic order is very strong, it can also destroy the topological band structure. So to have this all 3 parameter conditions met in one material is very difficult, and we'll show you how we realize this step by step. Of course, we encounter a lot of different problems. To show you just one simple problem, that is, all these topological insulating materials when we mention, bismuth selenide, bismuth telluride, they are not truly insulating. They are actually pretty metallic. This is because when the materials are grown, there are always defects in the material, in the bulk. And most of these defects donate charge. So that when you measure the band structure using ARPES by, say, Dr. Hassan's group or the exchange group, you can see the Fermi level actually cross a bulk conduction band in bismuth selenide and bismuth telluride. That's because the tellurium and selenium vacancies will donate electrons into the sample, so the bulk is highly conductive. In that case, you cannot distinguish bulk, surface, and edge state transport. This is why when we try to make this material magnetic and measure the quantum anomalous Hall effect, we found that although this material is truly ferromagnetic, but the anomalous Hall resistance at zero magnetic fields is very tiny. For example, in chromium-doped bismuth telluride, it's only about 50 ohm, and for chromium-doped antimony telluride, it's only a little more than 100 ohm. It's far several orders of magnitude smaller than quantum resistance. This is because you have a lot of bulk carriers in the material. But when we stare at these samples, this data long enough, we realize in this material, the ordinary Hall effect has a negative slope, meaning there are electron type carriers. But for this material, chromium-doped antimony telluride, it has a positive slope, meaning there are Hall-like carriers. Then we look at the band structure carefully. So this is band structure of bismuth telluride. The Fermi level usually lies in the conduction band because the vacancy of tellurium will introduce electrons. But for antimony telluride, the typical type of defect is anti-side defect, which donate holes. So the Fermi level lies in the valence band. So we thought by mixing these 2 materials, because they are very similar chemically, we may actually tune the position of the Fermi level very accurately. And at some point, if we are lucky enough, we will have a truly insulating material with the Fermi level lies close to the direct point. This idea is actually very similar to in the 3,5 semiconductors in gallium arsenide, aluminum arsenide. By mixing them, we can tune the energy gap almost continuously. So similarly, we have this band structure engineering technique in topological insulator where we can tune both the band structure and the position of the Fermi level. So we grow a series of materials from bismuth telluride over here to antimony telluride and perform ARPES measurement. So starting from here, the Fermi level really cut through the bulk conduction band. But as we add antimony into it, you will see the Fermi level moves down continuously towards the bulk valence band. And in pure antimony telluride, indeed, the Fermi level is very close to the bulk valence band. In this regime, with the antimony content around 0.94 and 0.96, there's a change of electron type DR cone to a hole type DR cone. So in this area, the bulk is truly insulating, and we can tune the carrier type by bismuth and antimony ratio. We performed transport measurement in this series of ternary alloys, and you can see in the 2 ends, pure bismuth telluride and antimony telluride, they are pretty metallic. But in the middle, somewhere around 0.94, the material is truly insulating. So over here, we already have a topological insulator. So 2 conditions are fulfilled. Then what about the ferromagnetic order? Then we try to dope with chromium. Actually, we tried several different kind of doping. Turns out chromium works the best. When we dope chromium into this alloy, luckily, we can see ferromagnetic order across the full phase diagram, not only in pure phase bismuth telluride and antimony telluride, but also in this insulating regime. You can see here we have a Hall type carrier, P-type carrier. Here we have N-type carrier. In the middle, that's an insulating regime, but the ferromagnetic order is still very strong. The TC of all these materials are around 30 Kelvin. It's totally insensitive to carrier type and density. This is very surprising because most ferromagnetic material, the mechanism for ferromagnetic order is RKKY, mediated by itinerary carriers. Then it's very sensitive to a carrier type and density. But in this material, as proposed by Fang Zhuan and Daixi, is due to the Fan-Fleck mechanism, which is from the band structure, not the itinerary carrier. So it's not sensitive to itinerary electrons, and it could be ferromagnetic in the insulating regime. So up to here, we already have a ferromagnetic topological insulator, and we know we are very close to the quantum anomalous Hall effect. But that's not enough. You can see now the anomalous Hall resistance is about 3 kilo ohm. It's still order of magnitude from the quantized value. The reason is when we grow this material by chemical doping, you can only get a discrete doping level, and the chemical potential is not very accurately controlled. In order to achieve that, we have to add a gate voltage. So now we grow this material on SrTiO. SrTiO is magical. It plays so many different roles together. It has a very large dielectric constant, so we can use it as a bottom gate to inject a charge into the topological insulator thin film. So still the same sample. In 0 gate, the anomalous Hall resistance is about 3 kilo ohm. But as we increase to a positive gate, the anomalous Hall resistance increases very rapidly. And up to about 80 volts, the anomalous Hall resistance is already 20 kilo ohm. And the upper bound is a quantized value. It's measured at 1.5 Kelvin. It's very close already. As we increase the gate voltage even further, the Hall resistance will drop. That's because now the Fermi level is tuning across the Dirac point. So more bulk carrier gets in again. So when we get this curve, we know we are already in the quantum anomalous Hall regime. All we need is dilution refrigerator, but we don't have one. So we send these samples and also our students to Professor Luli's lab in IOP, and where we perform the measurement down to 30 millikelvin, and immediately we saw this beautiful quantized anomalous Hall effect just expected in theory. This is a gate voltage dependence. There's a narrow range of gate voltage where the anomalous Hall resistance just stay at the quantized value, no larger, no smaller. So here's a summarized Hall resistance at 0 magnetic field as a function of gate voltage, and you can see there's a quantized plateau for this range of gate voltage. And meanwhile, the longitudinal resistance at 0 field also have this very sharp dip that's also consistent with the quantum Hall behavior, where we have dissipationless edge state. We also apply a strong magnetic field to see whether there's any change to the quantum Hall effect. And in this measurement, we have field up to 18 Tesla. You can see it's just a flat plateau, all the way from 0 field to 18 Tesla. Now we have new data up to 60 Tesla in a pulse magnetic field, still the same plateau, no change at all. And in longitudinal resistance, you can see at 0 field is already pretty small, but the strong magnetic field helps to have even better quantization. And above 5 Tesla, the longitudinal resistance is very close to 0 and stay there till 18 Tesla. So up to now, we have very strong evidence that the quantum anomalous Hall effect is indeed achieved, and later on it's confirmed by many other groups like Professor Kang Wang mentioned. And after the paper is published, there's a perspective by Sean O in Science called the complete quantum Hall trial. It means the quantum Hall effect, the strong magnetic field, quantum spin Hall effect discovered by Professor Molenkamp in 2007, and the quantum anomalous Hall effect have both been discovered. In fact, these two effects are pretty similar to each other because time reversal symmetry is broken. We have this chiral edge state. And the quantum spin Hall effect is different because it preserves time reversal symmetry, and there is this helical edge state. And recently, we got interested in the quantum Hall effect. So we want to go back and see the original report by Professor Molenkamp's group. Here's the data. Here's the sample. It's a mercury telluride and cadmium mercury telluride quantum Wall structure, which was predicted by Shouchun Zhang's group to be 2D topological insulator, and which they have this helical state. And here is the resistance as a function of gate voltage, and the broken line, the red line, is the quantized resistance, and the solid curves are the data. You can see the quantization is not as good as the quantum Hall or quantum Anomalous Hall effect, but it's not surprising, because when you have this helical edge state on the same edge, in principle, they won't get scattered if the spin is always preserved. But as long as you have any spin dephasing scattering mechanism, it will cause back scattering and destroy the quantization. This is why even for this kind of data, they need a very high purity sample, very low temperature, and in very small devices. It's a very challenging experiment. The original idea of Chaoxing Liu is if we start from quantum spin Hall effect, put ferromagnetic order into it, it may annihilate one of the edge state and change it into a chiral edge state and a quantum Anomalous Hall system. Now we have very good quantum Anomalous Hall effect. We thought, can we go back to use this to construct a quantum spin Hall insulator? So if you look at this, the two diagram, this is a quantum spin Hall insulator with a pair of counter-propagating edge state, helical edge state. And here we can actually use two quantum Anomalous Hall insulator if we can have opposite spin orientation and different momentum. We stack them together to form this bilayer system. Then we can call it a synthetic quantum spin Hall, because from the symmetry point of view, it's not a quantum spin Hall. Temperature symmetry is broken. But from the transport point of view, all the transport response expected for quantum spin Hall should be seen here. So all the applications, devices proposed quantum spin Hall can be realized by this quantum Anomalous Hall bilayer. So this is why we call it a synthetic quantum spin Hall system. So this is a schematic structure for the device. If we can have two quantum Anomalous Hall with opposite spin orientation and opposite momentum of the edge state, they may realize this is a synthetic quantum spin Hall. So what we do is we find two magnetic topological insulator with various different coercive fields. So in the strong magnetic field, they are aligned together, but with the reverse magnetic field, one of them is flipped first. So in this regime, we will realize this structure. So basically, it's two quantum Anomalous systems stacked together to form this bilayer. Then the next question is, how do we control the coercive field of magnetic Ti? So in recent years, it has been found that the chromium and vanadium doping into bismuth antimony telluride can both realize the quantum Anomalous Hall effect, but they have very different coercive field. Again, by mixing them together, we can actually tune the coercive field almost continuously. So in this experiment, we have a chromium-rich sample, which has a smaller coercive field, about 0.2 Tesla, and the vanadium-rich sample, which has a coercive field around 0.8 Tesla. They both have very nice quantum Anomalous Hall effect. So if we stack them together to form this bilayer, somewhere in the middle, around 0.5 Tesla, that will be the synthetic quantum spin Hall regime. So that what we found experimentally. We formed this bilayer, cut it into a Hall bar geometry, and measure the Hall effect, apply current from 1 to 4, and the measure Hall voltage from 6 to 2. You can see in strong magnetic field, it's very simple. It's two copies of quantum Anomalous Hall, which give you this half plateau. And when we reverse the magnetic field, in the immediate field regime, we will have this synthetic quantum spin Hall, where the two Hall channels cancel each other. We have this zero plateau. That's pretty easy to understand. Then we also did other non-local transport or multiple terminal transport. For example, we can measure 1465, is that simple 4-terminal measurements. And in the intermediate regime, if it's in the quantum spin Hall regime, the physics is very simple. Between any neighboring contact, there will be a quantum resistance because there's a pair of edges connecting them. So for this 1466, that's the diagram where we pass current from here to here, and between them, there's a quantum resistance. But because the device is symmetric, the current will split into two. So you expect to see a half plateau, which is exactly seen here. We can also measure 2-terminal resistance, 1414. there are 3 quantum resistors on each side. So the total resistance between them will be 3 halves. That's also observed here. So it's a very robust, nice quantum spin Hall response. We also cut the sample into a pi bar junction. So now it's asymmetric. So that's the equivalent electrical diagram. Again, the intermediate regime, we will find 1/4, 1/2, 3/4 quantum resistance, just expected from Landau-Bödecker formula for helical edge transport. So up to now, what we do is only to simulate the quantum spin Hall state using a quantum anomalous Hall bilayer. But this bilayer structure can also allow us to do more than that. For example, we can now measure the interlayer or inter-edge resistance between the upper edge and the lower edge. In the quantum spin Hall regime, these 2 edges will have different opposite spin orientation. So this resistance between them will be spin biased. Namely, it's a resistance between 2 spin species. And because the edge state is dissipationless, the potential here is the same as 1, the potential here is the same as 2. So the resistance between them is also quantized. So now we are having a quantized, spin-biased inter-edge resistance, and experimentally we see this 2/3 quantum resistance. It depends on how many electrodes you add on the other side of the device. So this is one project we have completed recently. We think maybe based on this, we can get more and more interesting devices and potentially some applications based on the quantum anomalous Hall effect. Up to now, when we talk about the topological order, it's a non-trivial topology in momentum space in the band structure. But we know actually in magnetic materials, there could also be non-trivial topology in real space, such as Skyrmions, which is a topological object formed by local moments. So when an electron travels through a Skyrmion, it will pick up a barrier phase because of the exchange of coupling between the actinium electron and the local moment. This barrier phase will act as an emergent electromagnetic field, so it will generate its own Hall effect, which is usually called the topological Hall effect. The experimental signature is a broad hump on top of the anomalous Hall effect. So this is well known for many different Skyrmion systems. And recently we found that also in magnetic topological insulator. The material system is manganese-doped bismuth telluride. Actually, we have studied so many different combinations of magnetic elements and topological insulators. The reason we want to understand this material is because the anomalous Hall effect has the opposite chirality from the chromium-doped one. So actually, we want to achieve quantized anomalous Hall effect with a different chirality, but we haven't done that yet. However, we found something quite interesting. So this is a 5 quintuple layer or 5 nanometer thick manganese-doped bismuth telluride. It's nothing interesting. It's just an anomalous Hall effect. But when we reduce the thickness just a little bit by 1 unit cell to 4 quintuple layer, and immediately we saw this very pronounced signature of the topological Hall effect found in Skyrmion systems. Then we reduce the thickness again by 1 unit cell to 3 QL, and the topological Hall effect is gone. It returns to the very simple anomalous Hall effect. So in this figure, I show the 3 samples together, the same material, but just different thickness, and you can see the creation and annihilation of the topological Hall effect. So somehow, the topological Hall effect is only stable at this particular film thickness for quintuple layer. So then the question is why? Why topological Hall effect only at this thickness? We have a simple theory about that and also some numerical simulation in this paper. The basic idea is in topological insulator, the DM interaction, which is responsible for the creation of Skyrmion, is mediated by the topological surface state. And when we make the topological insulator very thin, the topological surface state can actually hybridize with each other, and that will change the band structures, for example, open a gap at the Dirac point. And we know for this family of material, there's a transition, a crossover from a 3D topological layer with decoupled surface state to 2D with strongly coupled surface state. And that occurs roughly around 4 to 5 quintuple layer. So what we believe is happening here is that in this dimensional crossover regime, the change of band structure will have a favorable energy scale to stabilize the Skyrmions. So in this particular thickness, we will have the coexistence of non-trivial momentum space topology and also real space topology, and we can tune it actually by changing the film thickness. So we think that may also have some application in spintronics. So now I'll switch gear to a totally different topic. It's about ion-based superconductors. So these are the 4 families of commonly studied ion-based superconductors. And the most simple one is ion selenide, what we call the 1-1 system. Is just the ion selenium forming a layer by layer structure. So when Sequence Group saw this, they said, well, we must be able to grow this by using MBE and study its property by in situ ARPES and STM. So they choose this as a model system because it's so simple to test the mechanism for pairing in ion selenide. And this is their first trial. They want to grow this material on graphene because it's very easy. It turns out the coupling between ion selenide and graphene is very weak. The bonding between them is van Waals. So the ion selenides just grow into a tiny piece of nanocrystals on the top. To show you how weak the bonding is, they can actually use the STM tip to move this island as a whole. And you can see they can just push it a little bit from the edge and even rotate it a little bit. It's the same island. You can see this sort of a marker over here. But this one has the best crystals quality for ion selenide at that time. So they can perform very high quality STM experiment that already shows some very interesting results. It's the first paper they published back in 2011. They studied the DIDV curve on this ion selenide film on graphene, and they saw this V-shaped tunneling spectrum, meaning the gap is most likely nodal. Okay? A year later than that, Hanaguchi's group in ion selenide telluride single crystal, they found this very nice U-shaped gap. Both results have been reproduced by other groups. So they are true somehow by just increasing the tellurium content, you can change the material from a V-shaped gap to a U-shaped gap, maybe from a nodal superconductor to a nodal superconductor. That's already quite interesting, but not enough for Qi-Kun. Actually, back in 2008, he already proposed that maybe we can use the interface to find a generic approach to find a high TC superconductor. The idea is pretty simple and naive. If you just look at the Macmillan formula for BCS superconductor, TC is determined by the Debye frequency and also electron-photon coupling strength. For most metallic superconductors, it's conducting, but usually the Debye temperature is very low. If you want to have high Debye temperature to enhance TC, then you better have a ceramic or very hard material like diamond. But most of this material are insulating. So Qi-Kun's idea is, can we combine these 2 different materials, a soft metal on a very hard substrate? So in that case, you may have conducting from the metallic sample, but very high Debye frequency from the substrate, and probably very high, very strong electron-photon coupling at the interface. Then you have the advantage of both cases, and probably can enhance TC. That's a naive thinking, but he applied it to ion selenide on SrTiO. That works magically. So he tried to grow a single layer of ion selenide on SrTiO substrate, and he succeeded. You can see in middle already that the growth dynamics is very different from that on graphene substrate. On graphene, the sample wants to form this tiny free standing island. But on SrTiO substrate, the film growth is layer by layer. That already tells you the bonding between the film and the substrate is quite strong. Then he performed STM experiment on the first layer, the monolayer. Actually, he can have different layers, 1, 2 different unit cells, but it turns out only the first unit cell is superconducting. And when he performed the STM experiment, you can see the gap size is about 20 milliV. It's a huge gap. Remember, in this island of ion selenide on graphene, the gap is only about 2.1 millieV. So somehow there is a 10 times enhancement of gap size. That's the first finding. The second one is, now in this 1 unit cell ion selenide on SrTiO, the gap has a U shape. It means it's become a nodeless superconductor. So these 2 big differences tell us that somehow ion selenide on SrTiO is totally different from this freestanding ion selenide island. All of these discoveries by STM have later on been confirmed by ARPES experiment. For example, this is the work by Xinjing Zhou's group and also Donglai Feng's group. In this way, you can see there's a gap opening at around 65 to 75 Kelvin. So if you compare this gap size, it increased by 10 times. And the TC of this iron selenide is about 8 Kelvin. So by a simple counting, you will expect something around 70 Kelvin TC, and that's what's exactly observed by ARPES. And also the gap size in both experiments between 15 to 20 millieV. That's also very consistent with STM. Moreover, Xinjiang's group did the momentum space dependence of the gap size. It's highly isotropic, meaning it's not nodal. So all of these three results are consistent with STM. But there's always a question that are these gaps are really superconducting gap? Many mechanisms can give you a gap. In order to confirm it's a superconductor, you have to perform transport experiment to show zero resistance and a Meissner effect to show the expulsion of flux. But these are much harder experiments because STM and ARPES are in situ. They grow the film in UHV environment and do the measurement directly. But for this bulk measurement, we have to take the sample out of the UHV environment. So that's much harder, and we need to protect the sample. So in the transport experiment, they use iron telluride, which is an insulator, and can grow epitaxily from the iron selenide film and protect it and do the transport measurement. You can see the on-site temperature of the resistive transition is about 53 Kelvin. And for zero resistance, it's about 35 Kelvin, something like that. So it's definitely a superconductor and a high temperature superconductor, although the TC is slightly lower than what the gap measurement tells us. This was done by Yayu Wang's group in PKU. My group collaborated with the Donglai Feng's group. We also grew a monolayer of iron selenide. The difference from a Qikun sample is now the film is grown on metallic SrTiO substrate, which is much easier to prepare and has much better quality. But because this is a Meissner effect measurement, we can use a metallic substrate. So we put this sample in a two-coil mutual inductance measurement system. Basically, we measure the screening by this superconducting film. And the black curve is the data of a pure substrate without anything. It's nothing happening. And the red curve is this with this one monolayer and selenide on the substrate. And immediately, you can see the screening start from somewhere around 65 Kelvin. So that's highly consistent with the ARPES measurement of the gap size. Then the next big question is why the TC is so high in this monolayer and selenide on SrTiO. Then we need to look at the band structure carefully. Again, this is work by Xinjiang Zhou's group, where they measure the monolayer and selenide on SrTiO. The band structure becomes really simple. There are only two nearly degenerate electron pockets near the M point, and at the zone center, gamma point, there's nothing. There's not the usual hole-like Fermi surface pocket as seen in bulk iron selenide. The reason we believe is because there are very strong charge transfer from the substrate, from SrTiO to iron selenide, which will sink this whole type of electron pocket at that point. That will help to enhance TC to somewhere around 30 to 40 Kelvin, as people observed in other iron selenide system. But that's not enough to explain this is a 65 Kelvin superconductor. 2 years later, Yayu Wang's group also performed ARPES, very high resolution ARPES measurement on this iron selenide on SrTiO. They found something very interesting, and I think they summarized very nicely in their title of the paper. They claim that, well, they conclude that the interfacial mode coupling is the origin of the enhanced TC in iron selenide film. Basically, in this ARPES measurement, they see the replica bands for most of these conduction and valence bands, like A to A prime, B to B prime. And that's the shake-off bands, which is due to the phonon mode in SrTiO substrate, which couples to the iron selenide with only a small momentum transfer. And they think such coupling has an unusual benefit of helping superconductivity in most channels, including that mediated by spin fluctuations. So if I understand correctly, the spin fluctuation in iron selenide will give you an intrinsic TC around 40 Kelvin. Then from 40 Kelvin to 65 Kelvin, that's an enhancement due to the electron-phonon coupling at the interface. So this is what we call the interface-induced or interface-enhanced high TC superconductivity in this system. Okay, that's what I want to talk to you. Thank you very much for your attention.
right, thanks for that fascinating talk. How are we doing on time?
We are half an hour over.
I know.
So we will have a short break.
Okay, are we going to take a question or two? Okay, we have time for a couple of questions.
So I noticed in your hysteresis loops, some of them in the quantum anomalous Hall effect, they were offset from 0. Is that, you have an understanding of that?
Like what?
Like
this?
before that? Yeah.
Yeah.
So why is it the switching field plus 0.1 and minus 0.2?
Wait, I think they're the same. It's around 0.1 and negative 0.1. Here? They are pretty similar. They almost match it.
Shifted a little bit, but if this was in a high field magnet,
Yeah, it's made.
Niobium tin magnet, you can get tens of
Yeah,
millielectrons.
it's pretty.
Sorry, tens of millitesla trap. Oh, but I do see a little blip that's right at 0.
Oh, at 0, that's different. That's different. It's due
So
to.
I don't think it's trapped flux.
No, that's not due to the trapped flux in the magnet. It's due to the spin, the rotation of the domains. So as long as you reverse your magnetic field, the sample is highly inhomogeneous. There are some areas, small clusters, with hysteresis, corrosive almost close to 0. So they will reverse first. So we see this in many materials, but not all of them.
Experiment question about the anomalous Hall.
Yeah.
I noticed that at a 0 magnetic field, you suddenly have the I-axis, you see huge spikes. So suggests the system is like turning into insulator, right?
In
So
0 magnetic field.
0 magnetic field. You see, I see.
No.
No?
You shouldn't see that. Why?
No, you see here.
No, it's not 0. That's a corrosive field. Because the field scale is so large.
Oh, I see.
So you can see there are 2 peaks.
Okay.
Yeah.
Okay, it's not.
That's when you have have the domain rotation scattering between them.
I have a small comment. You have shown, like previous speakers before, the skipping orbit picture in the integer quantum Hall effect. The group of Klaus von Glitzing in Stuttgart has looked in detail where the current is flowing in the quantum Hall plateaus, doing, for example, scanning Hall probe. And they find that this skipping orbit picture does not apply at all. The current is either flowing in the bulk of the sample or in relatively broad stripes at the edges, but not in a skipping orbit mode.
Yeah, that's a very good comment. I think there are some experiments, for example, maybe in the Professor Exchange group, where they try to image the edge state or the conducting channels in quantum anomalous Hall insulator.
Well, the current flow has been imaged, and this has been published, and it's in the bulk or in broad edge states.
Oh, you have the data already?
Yeah, it's out. Yeah.
In quantum anomalous Hall insulator?
No, in the standard integer quantum Hall effect.
Yeah, I'm talking about the quantum anomalous Hall insulator. People are doing that, imaging of the conduction channels.
All right, so I guess we're going to take some time for some interfacial coupling, so to speak, and some refreshments, which we might have doped with chromium to make them even more effective. So when do you want to come back, Naichang? 15 minute break, so we'll be back in this room by 3:25. Okay.